To kick off our last major unit, we'll start with an overview of operating systems, including a little bit of history. And I warn you, the acronyms are going to get really dense here. By this time, we should have a reasonable idea of the hardware that underlies all our computers, particularly the CPU and memory. We're also very familiar with applications like Word or Photoshop or our Firefox browser or what have you. An operating system is what lets those applications work with the hardware. Some operating systems even allow the same application to work with multiple pieces of hardware. There are lots of operating systems, probably more operating systems than there are computer languages, although it's a close race. Now, there are things that are not quite operating systems and not quite hardware. They're sort of the interface between specific pieces of hardware and possibly a more generic operating system that might even support different pieces of hardware. BIOS on PCs is one of those. Every computer, Macintoshes, HPs, what have you, also has device drivers that help specific devices work with the operating system. And we've seen our programming languages, our compilers and our interpreters, that are also a way to make applications work through the operating system. But we'll focus on the middle. And we'll start with a little bit of history because, as we'll see, history tends to repeat itself, particularly in computing. Modern operating systems date back to something invented at MIT in the early 60s, running on some specific hardware from IBM, a 7094. It was called CTSS, the Compatible Time-Sharing System. CTSS, very specific to the IBM 7094, evolved into something that would be even more specific to its particular computer, OS 360 and the IBM series of 360 mainframe computers, which is what created IBM as the dominant computer player in the late decades of the 1900s. AT&T Bell Labs took a slightly different approach. They invented an operating system, Unix, and in fact they invented the language C to build Unix with. Nothing fancy about C, it just came after the languages D and A. I guess they didn't have to go on to D. And although this operating system was originally written for a computer called the PDP-7, built by Digital Equipment Corporation, some of you may remember that as a Massachusetts company, it was designed so that it could be ported or used on lots of different hardware very easily just by writing a new C compiler. Meanwhile, a guy named Gary Kildall, not Bill Gates, wrote an operating system called CP/M targeted on the Intel 8086 series. Actually, the first of the series was the 8080 chip, an 8-bit processor that could address, oh my goodness, 64 kilobytes of memory. Amazing. Now, you probably know the story of CP/M being taken over by Bill Gates and used as the foundation of MS-DOS, which is targeted for an IBM PC, but of course the IBM PC became a standard that anyone could use. MS-DOS, however, was still very focused on that Intel chip, the 8080 chip. Meanwhile, IBM took OS 360 to new heights and built in most of the technology that is even now the foundation of all modern operating systems in a system called MVS. Practitioners of the Unix religion underwent a schism. The University of California at Berkeley spawned one version, known as BSD, and AT&T held on to their own version, which they referred to as System 5. This schism still has some implications for us today. A schism also happened on CP/M, where Stephen Wozniak took CP/M from the Intel 86 and ported it to the Apple II's processor, which was a chip made by Motorola. The portability of the Unix operating system led to lots of companies using it as a basis for their own proprietary hardware. Sun, HP, IBM, lots of others. It also led to the creation of the first open source operating system, Linux, which was a version that anyone could see the source code for and use with no charge, and enhance as well. Apple took a different approach, and instead of pursuing portability, tied their operating system even more tightly to the Motorola hardware using graphical interface techniques that were appropriated from the Xerox Research Center. The success of that graphical approach forced Microsoft to put graphics into their MS-DOS version with Windows, and even the Unix community, via the Sun operating system Solaris, started working on graphical approaches as well, all very different, of course, from the Mac approach. Given its portable nature, the tentacles of the Unix community spread widely in the 1990s. Through AIX, they even infiltrated the IBM mainframe operating system environment. They also, through Steve Jobs' company Next Computer, infiltrated Apple and were the key to getting the Mac OS X version of the Mac operating system to work not only on the rapidly becoming obsolete Motorola processors, but also on the Intel architecture. Windows NT, although it didn't actually steal anything specifically from Unix, took lots of the ideas and, although not making it portable, adopted many of the operating system characteristics. All of those chains there still exist today. There hasn't been a lot more intermingling going on, although we may start to see some of that again in the future. And all of those operating systems have basically the same level of capabilities, with the exception of IBM, who continues to still push the state-of-the-art. Solaris, although it's in turmoil right now with Oracle, also had some great ideas in those environments, and we'll talk about those a little later on. So, operating systems are key. They made IBM, arguably. They made Bill Gates and Microsoft, definitely. And the combination of innovative operating systems and hardware made Apple. So we see them on personal computers. We also see them on big servers even today. We think of them as file servers or compute servers, but the IBM systems are still what's used to process the transactions in the New York Stock Exchange, book most of your airline reservations, and do the heavy lifting in a lot of banks and financial institutions. There are also operating systems elsewhere. There are operating system wars going on right now in your cell phone. At the bottom of this slide, you can see there are actually 5 operating systems primarily used on cell phones today, duking it out. 3 of them are variations on the operating systems from the other systems. 2 were basically following different threads, the Symbian and BlackBerry operating systems. Interestingly, those are the older ones now that are losing market share to iOS and Android. And operating systems also exist on your routers that run the internet, on robots, in cars, in your microwave oven, and they're taking over just about everywhere. Those last 4 categories have something that's very distinct from the first 2. They have what's called real-time constraints. If your cell phone doesn't respond to the local cell tower in a particular amount of time, the cell tower will assume it's been turned off and disconnect your call. How many times has that happened to you? A router on the internet will drop packets if it doesn't respond quickly enough to the person who sent the packet. A robot, clearly, if it doesn't get control of its feet or its arms or its transmission quickly enough, can fall over, lose its balance, or even destroy itself. And needless to say, we don't want to be waiting a long time for response time when the electronic ignition in your car is being used to pass the local semi-trailer. So, real-time constraints mean that these operating systems have to fit some very different design models than any other things. That's one of the challenges that people like Android and Windows have had in taking their previous multi-personal computer operating systems and making them work on phones. Now, we've also seen a move in some cases, particularly at Westwood High School, to what we call thin client architecture. Instead of having a personal computer that has a single user operating system, we actually put all the meat back on a centralized server and run what are called thin clients. They're a lot cheaper to maintain than individual PCs. This has been taken to the next step in something that's called cloud computing, where save your files off in the network, Google Docs, Google Calendar. Don't bother to put them on your personal computer. So if we think about the computer with its memory, its CPU, and its I/O devices, and we're also going to talk a little bit more about information in the files that it stores, we can see that multiple user systems, or time-sharing systems, need somebody to make sure that all that stuff can get shared amongst the multiple users. Even on your own personal computer or on your cell phone, you're also probably running multiple applications at a time. You've got Facebook up to keep track of what's going on at the same time you're using Microsoft Word to prepare your local English paper. Don't lie, I know you do it. Amazingly enough, this idea of keeping multiple programs running at the same time or simultaneously is known as multi-programming. And actually, in its more general form, it's the origin of the term multitasking, because a process or a task is really a program while it's executing. In some cases, a program may have a couple of tasks that are involved in keeping it executing, or we may have multiple copies of a program, each with its own process or task. The key here is that there's only one CPU. So really, at any instant in time, there's only one process that's actually executing. But the operating system is in charge of making sure that each process thinks it's executing all the time, and it's the only one on the computer. So cut to its essentials, the purpose of an operating system is to manage those limited resources of a computer so that multiple users, or multiple programs, or both, can share them nicely. Everybody's familiar with sharing, but the operating system tries to maintain one additional fiction. Everybody has their eyes closed, and they don't really want to know that anybody else is sharing with them. They just seem to think the soda's going away a lot faster than they're getting it.